All right, welcome everyone. Thank you to Lab Manager for the introduction. Thank you all for being here. We're going to go ahead and jump right in. If you've got questions, please do leave them over in the Q&A section, and we will try and get to them towards the end of the presentation. What we're going to be talking to you about today is sort of a practical walkthrough of getting started with using some machine learning techniques in your laboratory. And some of the tooling and processes that might help you get started there. So, very sort of to set the stage, we see two kinds of clients. They tend to come from a large organization where there is a clear demand to do machine learning and AI, but it's usually part of the data science team, and you may not have direct access to it as a laboratory specialist. Or in a smaller organization, we know there's demand. We've had discussions at at the previous lab manager leadership summits and these sorts of forums where it's very clear there is a demand and a desire to be using some of these more advanced computing techniques, but no path to get there. No idea of how to get started and no clear direction for where to go. So some of the common barriers that sort of keep you from getting started, you don't have enough data yet, or it's messy, or it's not well labeled. And it's unclear what value you might get back from, say, a machine learning project. So there's no practical path to an implementation. You don't see how to get started, and so you never get started. What we're hoping to do today is convince you that you do want to access some of these tools and that we have some relatively off-the-shelf bits of software and ideas to help you get started. So why do you need this? As we are looking at the data streams of most of our clients, what we're seeing is that almost everyone has very high dimensional data and more of it than you are readily handling by hand. It's getting harder to wrangle it manually, and you need some of these better tooling to start to help. And then there's the analytics side of this, and that is that it's easy enough if you only need to work in 2 or 3 dimensions to do your analysis. The machine learning techniques that we're going to talk about today quite happily scale up to tens, hundreds, thousands of dimensions and give you access to a richness in your analytics that's just not possible if you don't start from some of the more advanced compute techniques. So what are we going to do? We're going to start with some image flow microscopy. And you're seeing an example of the images we're going to be looking at up on screen. These are from a Yahara client, some friends of ours that generate this kind of data pretty routinely. And we're going to hope that that's a reasonable stand-in for something that you've got in your laboratory. So the intuition here is maybe you're generating this kind of particle data as a way to evaluate the quality of an assay that you do routinely or some batch-to-batch manufacturing tolerances, and you want to start to look at this and use this data at scale. You've got a bunch of these images laying around, but they're not well labeled. They're just images. If that's not exactly your use case, bear with us for a little bit. But hopefully some of the techniques here are more broadly applicable. And we're going to start taking you through what would it look like to build some machine learning around these. So Adam.
So when you start off on an initiative like this, it starts with planning. And initially, what questions are we looking to answer? That's going to differ regarding the laboratory, the type of science you're working on. But as James alluded to, the techniques, the process that we're going to talk about today is applicable to most of those types of projects. And so what the question that we're going to look at today is going to be a simple one of classification of images that can be expanded to as I said, a myriad of data. And once you have sort of that initial set of questions, we need to start with the organization. What data do we have? How is it labeled? How are we identifying it? And how do we set that up and prepare to feed that into the learning algorithms that we're going to explore? And we'll walk through that process. And want to highlight the fact that this is an exploration. As you get started in this type of process, finding a model that fits your needs, it will be data exploration. It will be a bit of data massaging, analysis, and exploration into the different techniques that might work best for the problem at hand. So as I said, for today, our goal will be to show what that process might look like to answer the question, what's the best method to have a machine learning algorithm categorize individual images based on their shape. So we're going to start. Here's an example of the data that we'll be looking at today. On the right-hand side, it's an array of particle data. And ultimately what we ended up saying is, can we create a machine learning model that can classify these images based on their shape as a circle, a rod, or a spiral? So straightforward and simple as that, to demonstrate the techniques that you would follow to build one of these models. Now, when you get into sort of organizing around that, there are some common challenges that you might run into. You might not have data. You might not have enough data. It may be inconsistently labeled or organized. Maybe it exists on different people's laptops. Maybe it needs pre-processing. Maybe it's time consuming or error prone to do the labeling that is needed. There are a lot of different initial hurdles to think through. And again, this is that exploration phase, that idea of working through the data that you have and understanding how best to get it manipulated to feed through these algorithms. And what is the time that's involved in that, the investment? Do you need to go out and source data? How long does it take to label, and how do you reduce that? So those are some of the questions to be thinking of as you're starting to look through data.
And Adam, I want to jump in there and just point out, the laboratory is one of the most data-rich environments we have. And routinely what we see with our laboratory partners is we throw away almost all of the data and keep only the final result and put it back into your LIMS system to report. You have large quantities of unlabeled data. Even if you haven't looked at them recently, they're laying around, they're generated by every instrument. This should apply to something in your laboratory. It's all there in your current process. And
as James said, in that process of storing, throwing away, losing, chasing data around, you might start with at a point where it's not ideal. And for our example, we started with a set of these image montages. With very little metadata. We wanted to demonstrate this idea of, okay, we're starting with really not a lot of context here other than a handful of these images. There's about 600 individual particles represented here. They're irregularly sized, which is not ideal, generally speaking, particularly when we're talking about convolutional neural networks and things like that. You'd like things that are a little bit more uniform. The format here is irregular, and even to get the data out of this, we're going to need to do a little programming, a little extraction. So, really at this point, we're looking at a large amount of data that needs some attention, and really we only have 1 or 2 points of metadata about it. What experiment did it come from? And from there, we need to get to a point where this is usable to feed into the machine learning algorithms that we're going to test. And so what does that mean? Why do we need data that's structured and processed in such a way? So let's talk a little bit, stepping back, about how data is used in supervised learning algorithms, which is what we'll talk about here. And what that means is we're going to feed it data that we already know the answers to the questions that we're trying to ask in the future. So we're going to take a sampling of data, give it to the algorithm to learn and train on, and hopefully come up with a model that can then take new data and make inferences about that are accurate. So we start with this raw data. That's our image montage, and we'll need to manipulate that and pull that apart and give it labels. We'll need to give it features, metadata about those individual particles that characterize them. And to train a model on that, then we'll need to split that up into these different categories. And so we'll talk about these as we go along. But your training set is really kind of the core data that you're using to train a model on. So you'll take that labeled data and split it up, say between a training and a validation set and a test set, in particular percentages, depending on what you're doing. But that training set is really what is fed into the algorithm of choice. And in the training process, it will try to learn, it will try to generalize predictions. In our case, what's the probability of this being a circle or a rod or a spiral? And it will come up with a set of internal values that it thinks are representative. And then we'll evaluate that on what's called the validation set. So this is the data that says, okay, based on what you learned, your accuracy for making these predictions is, say 70%. And then, part of the model building process is then going through and doing some internal adjustments and saying, okay, well, how do we make that better? And we'll go through these epochs of learning and updating and evaluating that to try to get to a high percentage of accuracy. And then ideally what you'll have is some set-aside data, a test set at the end, where once you have, you're fairly confident in your model, you can evaluate that against the test set and say, okay, yes, the accuracy against data that it's never seen before, that's representative of real world data is, say, 75, 80, 90%. And there are a number of different ways you can evaluate models. We're going to be very simplistic here. We're going to talk about, high level accuracy numbers. We're not going to get into too much detail. That could be, a whole other webinar in itself of getting into like the nitty gritty details of evaluating models. But for the purposes of talking through and demonstrating this initial exploration, that's a good starting point. And so that's what we'll use as our baseline metric. So with that in mind, we go back to that idea of the image montage, and then how do we start applying labels and organizing this data? So in this case, we brought in a tool called Label Studio. It's an open source application. And what that allowed us to do was to do a little bit of hand labeling of the data. Like I said, we only had a couple points of information about the image montages. And so we wrote a little Python code to extract those images out of the montage. And we started out with this idea of, okay, well, let's categorize it by some sample type. Let's give it some shapes, a grouping. Weren't really sure where that might go initially as we're looking through this. And even that process, the initial process of labeling might give you different insights into the data that you're investigating, though you might have data that's well known. But in our case, you'll see, we have a number of different shapes, and ultimately we didn't use all of those. We just decided, well, let's just keep it simple. We'll do three types. Loaded that data into Label Studio and painstakingly manually went through each one of these and gave them labels.
This is slow and tedious and time consuming, and maybe you have to do some of that to get off the ground. We're not going to stay here
somewhere,
but you need to start somewhere, and this is an approachable way to do that.
Having tools like Label Studio can be a benefit to that. It can help start to organize these. Once it's done, you can export that data into out into JSON or CSV formats to be used, and we will show how we're doing that later. But we must get started somehow, and this is what we did. But at that point, we had roughly a bit over 1,000 images that were labeled. And that took, an evening of going through and doing that hand labeling. So as James said, very expensive process. And still, we didn't have that much data. So how could we get a little bit more metadata? We want to demonstrate in this process both, looking at the images directly, but also how can we do some training on metadata about them. And so James had the idea of, well, let's turn to AI. Let's turn to a large language model. Let's bring in ChatGPT or Claude and see what it can do. And so he did a little experiment there, asked Claude to generate up some code that would look at these images and extract some metadata about them. And so what it came up with was the use of the OpenCV library, which is an image processing library available in Python, that would take the original images, do some, look at some thresholds, do some contouring, and ultimately generate some additional parameters, additional metadata about the images that could be interesting. So things like the solidity, extent, circularity, aspect ratio of the images. And again, we're in the exploration phase. So we're saying, well, what can we generate out of this, and how might we be able to use that to build a good model?
And to be clear here, I did write code for this, but I wrote very little of the code. Mostly, I started from the images and I asked the AI to write me standard coding techniques, use standard open source models, and generate some data. Again, just something to get us off the ground. So at this point, yes, there is code happening, but it's not very much, and I didn't write very much of it.
So starting with that, now we have our set of images. We have some additional data about them. We want to start building models. How do we do that? So here we turn to a few different libraries. We're talking about here TensorFlow and Keras. So TensorFlow is an open source machine learning platform, very, very powerful, very popular. And Keras is a higher level API for manipulating TensorFlow that's a little bit more approachable by us mere mortals. And it makes it very simple to take common machine learning algorithms and apply them to your data. So, what we're looking for here as a way to quickly and easily start validating some approaches. And so TensorFlow and Keras is a perfect example of, tooling that we can use to do that, to make it a little bit easier for us. And as I said, the reason this is important in, the laboratory setting, in this early experimentation setting, these let us build our models using, existing Lego bricks, if you will, existing well-documented, tested code to run and evaluate our models. No reason to reinvent the wheel, get down in the weeds at this point. Later in life, if we have a promising methodology, promising set of models, there are opportunities to tune and make those better using, closer to the metal with TensorFlow or other image processing APIs. But here's where we're going to start. It's a great place. We'll also bring in some other tools along the way, scikit-learn, which has some of the more simple machine learning models that we can use to do some early validation. So you'll see that as well. And with that, we can kind of start jumping into the methods and the codes. We're going to kind of go through a series of these experiments that we ran to compare a few different models to one another, starting with logistic regression. And James, you want to talk a little bit about why we chose this and what's happening here?
I do. So just a little intuition for why we start here. We'll show you some results from some very simplistic classification mechanisms that are much more black or white. They just give you an answer and really no probability on top of it, no transition between sort of two values. You just get an answer out. Those have strange performance characteristics as you scale them up, and it's hard to validate a lot of the time. So the logistic regression is a smooth way to get from 0 to 1 on any given category. That's all we're using it for here. So it really is just a nice smoothing function that lets us have a gradual transition between two values, and we can start to put more statistical confidence on our metrics because we are using that as our fundamental building block.
So what does that look like from a coding standpoint? We said we're going to have to write a little bit of Python. So this is just a little bit of Python.
And this is the whole script. Even
not
if
quite,
you don't
not quite the whole script,
well,
but almost. We're pulling in a couple common libraries that I'm sure many of you have seen before. Pandas, NumPy for doing some manipulation of the data. Scikit-learn for, in this case, our logistic regression model, and doing some data splitting of the data sets, and then we'll show a confusion matrix later. So some simple code built in to do really all the things that we need to do to load our data, evaluate a model against it, and display the results. We're loading some data sets. We've elided the code that sort of ties these all together, which was quite frankly the bulk of it. and then finally we're splitting the data here. Again, we talked earlier about our training and our validation sets. We're splitting them out into training test sets so that we can run the logistic regression algorithm against the data, fitting it against our training data, and scoring it against our test data.
And to be clear, the reason that we're doing this, you're going to have to do a little bit of coding, but we want to make it clear that it's pretty low barrier to entry. These are very standard techniques, and this is not a high hardware requirement. The majority of this work is Atom on a generation old MacBook. That's it, right? That's all the hardware that we need to pull this off.
My MacBook's a little sad you're calling it old.
It's only one generation old.
So our results for this, again, we'll talk about our sample size, right? We started with 1,400 or so records. We threw it through the regression algorithm, and we came up with an accuracy of prediction of about 75%. So not starting too bad. We're showing our confusion matrix here, which if you haven't seen this before, we like to see nice dark blocks on the diagonal, meaning that the expected label and the predicted label were the same. We've got a little bit of variance here, but not too bad. And for a first go around, okay, well, this is interesting. We've got a baseline. And I will say, I think I omitted saying this. So what we're doing here is we're running this model against the metadata that we generated from our labels and from the OpenCV code that James and ChatGPT put together to extract our values. So where do we go from here? James, did you want to?
I was going to point out simplest possible model, okay results pretty quickly. This is a starting point for iterating. And this is where we're doing data science. and it's just science, right? We should be able to experiment and do better than this. And the intuition is we just need a starting point, a baseline, somewhere to get off the ground. That's what you're looking at.
So we're gonna kind of chase two things here. We're gonna look at sample size a little bit later, but first of all, we're just gonna look at different algorithms for doing this. And the next would be random forest, which is another fairly simplistic type of machine learning approach where you have a couple different decision trees, doing some analysis and trying to come up with predictions, maybe a little bit more sophisticated than logistic regression, but still very simple, very fast. And we'll look at the code here. And what I'd like you to note is that this is really the only difference between those two scripts. Or instead of logistic regression, we're using a random forest classifier, and we're essentially doing all the same things that we were in the previous example to give us a set of results that are surprisingly accurate. Now, I would caution, given the sample size that we have, that one would want to take this and test this against a lot of other data, much larger sample size to see what happened. But what we wanted to show here is the act of picking the right algorithm might be, there's no right or wrong answer. There's a number of these approaches that can be taken. There are ensemble approaches that can be taken, with many different approaches, but you're going to see a degree of accuracy. And I would also caution at this point, when you see something like 93% on a small data size, you should probably also consider this with a grain of salt.
It means nothing. It's interesting.
It's interesting. It's giving us a little bit more data to fill out our intuition as we move forward. So the next thing is we'll move into neural networks. Let's see what a neural network does. You've probably heard about those if you've read about AI and machine learning. It's a little bit more sophisticated way of taking this concept of neurons that take inputs from previous layers. So, we're going to start out with the features. We're going to feed those into a layer that does some calculations, passes that on to subsequent layers, and comes up with, at the end of the day, again, a prediction of, what's the probability that each one of these images exists in a particular class. And again, when I say neural networks here, but we're still just working against that same CSV data that we've been using for the linear regression and random forest classifiers.
And it's worth pointing out, a neural network, the under the hood architecture is basically multiple logistic functions, right? Many.
So I'd also like to point out here, so we're using a very simple network here. Everything that we're going to show you today are examples that are, kind of well-known architectures or, simplistic, kind of like you will see these in introductory books to machine learning. And part of that is to kind of show that the sophistication, the sort of barrier of entry doesn't necessarily have to be that high, right? You could go and you could tune these and do a lot of methodical exercises and, analyzing what might be the best, network architecture for things like this. But it's relatively simplistic to start off. The code, as you see here, is not a lot different from what we have just looked at. There are probably some things that are new here. There's an activation function. As James mentions, that's the function that's tweaking values in each of the neurons. There's a loss function that's helping the algorithm decide, how good its predictions are over the set of data that's testing. Optimizers. We're not going to go into any of that. Again, that's deep down into the forest, and we want to keep it high level. But I think what's interesting to note here is If you're looking at the model summary here, it's giving you an output of layers that you have, the number of parameters that are going in there. And as you can see, with just a few layers, our parameter counts, the number of calculations that are associated, with each one of those is kind of starts to explode and come back down. And as you might guess from seeing something like that, large networks start to involve lots more calculations, which means the processing, the learning times for these types of networks will start to grow. That said, this still runs very, very quickly on my old MacBook Pro.
And it's worth pointing out that we started this by saying your data is higher dimension than you can work in as a human. This is how the machine is handling it. It's got a way larger number of parameters that it can tune. We're going to train those. We're going to learn our data set.
And in our results here, you'll see, again, some interesting results. Same sample size. Our accuracy during training was about 73%. So that's the accuracy against the training set data that we're using. When we're talking about neural networks, and we'll talk about convolutional neural networks next, these are a little more sophisticated. They have a different training cycle, and we have some additional data to show as the algorithm trains over what are called epochs. So that's kind of the cycles that it's training. And that validation accuracy is, again, our accuracy against some of that validation training data that it's using outside of the cycle to validate itself. And so the correlation between accuracy and validation accuracy is something that we're going to look at, because when you see those differing, it can tell you a little bit about how the model is working. And when you see big variations, what you can kind of learn from that is perhaps the algorithms kind of memorizing, if you will, overfitting. It's called the training data that it's using. And not generalizing well. And so we see a little bit of that here, though, they're relatively close. But you can also see our accuracy has dropped way back down. This was not as accurate as the regression of random forest. So this is to indicate that it doesn't necessarily mean that, because a method is more complex, that it's going to be better. Sometimes it's worth trying some of these smaller data sets to see what happens.
I think we can also just intuitively looking at that training graph, I don't have much confidence in this version of the model. The crazy spiky training progression, this is not working, right? This is not giving us a good insight into our data right at the moment. So that's one of the intuitions you can pick up without doing a lot of deep analysis. That's a strange training graph.
Right. And you'll see the green and the dotted red lines there, that validation accuracy and the accuracy, they're not really changing much over time, right? That hasn't really, evolved much as the epochs have gone on and as it's learned. So definitely we're going to see if we can't do better. And so at this is point where we're going to kind of maybe take a fork in the road here and say, okay, well, it was interesting to look at the data we generated in spreadsheets and using OpenCV, but let's refocus on just the image data itself. Let's look at convolutional neural networks, and these are designed to take the image data itself, so the pixel values, the intensities of color, and analyze that through some internal mechanisms to detect features within the image, and then try to do its categorization using those features. And this is where, again, we're gonna go back to taking some fairly standard CNN architectures. That is again another one of those topics that's relatively complex that we don't want to dive into the details of, but we do want to talk about how these can work for specifically image data, or it doesn't necessarily have to be image data. It could be other things. It could be speech, other waveforms, things of that nature. And then I guess, James, did you want to talk about anything we're here before we start launching into
No, just let's keep going.
So again, as I said, that CNN is going to take as its input parameter this input shape, the image itself, unpack that, take that array of pixels and run it through the set of layers. And again, this is using what's a fairly standard simple architecture for a CNN, and put that together, compile it, and we'll run our models on this as we have some of the others that we've shown to get us.
Go back to that slide for just a second. The intuition here that I want you to have is stare at the images and tell me which ones are a circle. If you can see it, the model should start to see it, right? That's your intuition for what this model is doing.
So as you can see with our CNN, so we're actually getting an astounding 98% accuracy, but only a 72% validation accuracy. So
don't trust it.
So here again is where we see, we can plainly say the model has overfit the training data. Its validation accuracy is actually almost as bad as everything else that we've used. So no big gains here. Plus, it's a lot of additional complexity. It takes a little bit longer to train, though. Again, not a ton at these, this sample size. So let's go back and start thinking about the size of the data that we have available to us, and how might that change our approach. And when it comes to data, as you've probably all heard, certainly if you've been to any of the talks that James and I have done, a lot of this is about the data. The more data that you can have, the better. The more representative the data is, the better. There is a lot to be said there about how to prepare your data, how to make it available, problems, caveats, things you need to think about along the way. But at the end of the day, with 1,400 samples, we just need some more. And we're recognizing the fact that if we were to go through and hand label all of the data at our disposal, it might take us a couple of weeks and we would never have made the deadline for this presentation. So how can we speed that up a little bit? What do you do if you don't have enough data? You need to generate it, or you need to come up with more. Maybe you need to go buy some, maybe you need to, whatever it takes to gather, but that might be, limiting. That could be costly. You may not have that. So can we bring in some other methods, try some other methods to help us get our training set larger? And so we wanted to run through some fun examples here and look at maybe compare two things that you can do if you just can't get more labeled data available to you, which is, again, augmenting the data yourself or synthetically generating some. And so one of the things that the Keras library gives us is some image pre-processing. And so one method, one simple method of augmenting the data that you have is to run it through a data generator or pre-processor that can take the images you have and make small adjustments to them and use that to feed into the training algorithm to give it more variation in hopes that it can generalize on features a little bit better, and perhaps that gets us away from the overfitting, the overtraining that we're doing on the small set of data, and generalizes better on real world data.
It's a very common recommendation in the machine vision space, is to do something like this. How's it work for us?
Well, so, we're with some simple approaches here. We're going to do a little rotation, some shifting of the subject matter, some flipping horizontally and vertically. And when we do that, we see about what we expected. So again, a little asterisk by the sample size. So what's happening here is every epoch that it's training, it's going through and doing some image manipulation, training on that, and then kind of cycling. So it's seeing different variants of those images every time, but it's still only seeing about 1,400 images. Our accuracy is still high. Our validation accuracy is a little bit better, but not significantly. And so I think we're still suffering from the same issues that we saw before. And also, as you see the graph of the training and the accuracy numbers over time, they're still all over the place. This isn't looking great. So a little bit of improvement, but not enough to help us out here. So try two. What happens if we have some synthetic data? And in this case, we said, well, how could we generate this? And again, we went back to AI and said, well, could we use an image-to-image model? So that is a model that can take an image and generate variations of it and use that to augment significantly the amount of data that we feed in. And so again, we went back and said, in this case, Claude, this is what we want to do. Can you help us sort of write a little code around this to create an image generator script that can augment our images? And did. And so what we ended up with, the output is what you see on the left here. So these are all synthetically generated images from that process. And you can kind of compare those to representative images from the original data set on the right. They're clearly different. They have a lot of different artifacts. Certainly, as you stand back, you say they're definitely not the same. You can almost tell they've been kind of created by an AI. But they do represent the ideas, and that's one of the things that's important in CNNs is it's looking for features. So if we really up that image or that sample size, we expect it to do better. And so generating those images took we actually threw this on an NVIDIA card of a 3070 that I had at home. So not a huge graphics powerhouse, but a little bit more than the MacBook. And generated ourselves a much larger set of data, in this case, 16,000 some images, and came up with a very pretty graph here. So we see a 97% accuracy on the training data, and we've got two numbers here in the validation accuracy that I want to explain. The 96 is the training data that was separated out from that original 16,000. And when you look at this graph here, you're seeing something that looks a lot more like what we'd want to see. Our accuracy and validation accuracy are kind of going up and plateauing over time. And the 97 and 96 are very closely correlated. So it's doing a good job across those data sets. And now that 85 number was a holdout set that I took from the original images that we had. So we didn't use any of the original images in that sample that was sent in to train the model. I used those to fit against the resultant model that came out of that. And it came up with an 85% accuracy. So what's interesting here is, we're seeing about 85% accurate application of that model to the real data. And that was a little bit of an improvement over what we've been seeing with some of the other approaches, given a much larger data set size and a different data set size. And so, there are some trade-offs there, but it's an interesting result to say that, with significant amounts of synthetic data, we can tweak that number a little bit. And it might indicate that if we had a larger, sample set of original images, well, maybe we can do better yet still.
And it's worth pointing out the intuition here. We're still a little suspicious of those high accuracy numbers because the holdout set being significantly lower is not great. So higher number, not necessarily better. I'd rather have those relatively high and matching. Still a little suspicious.
Yes. So then how do we get ourselves more real data? And so we took an iterative approach to this. We certainly weren't going to spend a significant number of evenings going through and hand labeling that. But we had an idea. Well, what if we take a small set of images? What if we start off with 400 and we build a model off of that? And then we fit that model against the rest of the data that we have and simplify our labeling process. So the output of that is a bunch of images that have a high probability that they're circles. And we pick from those the best of the best. It's like, oh, that's easy because I can go into like the file system, show me the image, show me the images there, and just, quickly pick a few hundred images and then create a more refined data set that I feel really good about, that has like, these are great representations of circles, these are great representations of rods, and so forth. And then take that and use that larger data set as our starting point to create a new model. And do this iteratively with this human in the middle, us, at each output stage, saying, yes, it got these wrong, but these are all right. And so I'm kind of feeding forward this better training set of data. And ultimately, we were able to get ourselves a much larger set of initial data and a much nicer model. So this is our graph of the final model that we created through that progressive process, where we're seeing really what we want to see, which is, accuracy and validation kind of going up and plateauing at a reasonable number. In this case, what we ended up with was about 84% accuracy on those 5,000 images with 82% validation accuracy. So we've really closed that gap. We feel pretty good that this model is generalizing better. And of all the different approaches that we took, having that hand-picked data set that we felt really good about with real images, a larger data set, really did give us the best results. And as we perhaps had intuition in the beginning, really looks like the best way of going about it. But the process of being able to create that larger sample size was something we had to work for and put a little bit more time into.
These big data exploration projects, they take time because you do have to get down in the data and muck around a bit. You're going to have to try some stuff. Notice we tried 3 or 4 different things. We tried improving some of our approaches, and it's sort of the last one that ends up working. But you don't necessarily know you should have started with that. That's not something I think we would have done day one. So
because that would have taken a lot of time, right?
Yes.
And we wouldn't have known necessarily out of the gate that 5,000 images would be a great number. And we could certainly do better. And I'd also like to mention that this is a starting point. We created a set of these models. We validated them, or we tested them against one another. We got some of this data. There's still much more that you could do to refine these models by tuning them in various ways that we don't have time to get into. But at the end of the day, we have a pretty good map here of methods, some different sample sizes, different ways of getting at that can kind of point us in a direction of this is our best bet, we think, at tuning these going forward.
And your intuition here is that 84% on the accuracy is probably real because we started with messy data and we don't really expect to be perfect even against the training set. There's too much noise in the data itself. So this is the first time that it starts to feel like, yes, that's a useful model and a good starting point for further training.
So with that, I guess, James, you want to kind of wrap this up?
I do. I want to pull us sort of back up to our example. We started down this path because we said we wanted maybe a way to do some batch to batch comparison. So, this is maybe an assay we run as we're in the middle of a manufacturing process, and we just want to get a feel for, are we creating the same kinds of outputs over time? Are we seeing consistent evaluation? And you're starting to see a pretty quick path to a deployable model that we could actually do something like that with. It takes a little time. You have to go spend some time with the data. We did have to write some code to pull this off. To Adam's point earlier, it is very standard techniques. This is machine learning 101, first 10 pages of the textbook kind of stuff. We're really not digging deep on the kinds of depths of information that you could get to here. But you do have to go spend some time down in it. And as you are starting to pull this back up and say, okay, is this useful? Do I have a path forward here? We want you to reflect back on the data that your laboratory has that you are not leveraging right at the moment, and ask, could I be getting value out of that? Is there some way that I could be evaluating it, monitoring it over time, learning from it? And even if you are not doing particle image microscopy, you should have something like this floating around. If you don't have the expertise in-house, that's sort of what we're out here to help with. But we're hoping that just by starting somewhere and being willing to explore and work on your data a little bit, it starts to become obvious that the gap between I have data and I want to be using machine learning is maybe not as big as it looked. This really was just Adam and I working through some. That's it.
Great. Well, I think with that we can start moving on to questions and just maybe a little bit of a call to those of you that might want to talk more. In a couple days, on Thursday the 11th, I'll be doing some office hours from noon to 2 Central on Zoom. If you're interested, go check out the QR code, give me an email, drop by. And I think we've got a few questions from the.
If you haven't posted your questions yet, we're still taking them. And if we don't get to them all, we'll contact you out of band and address them that way. Laura, we lost you.
Oh, I'm here. Yet great presentation. Thank you so much, Adam and James. At this time, we're ready to move into the questions and answer part of our webinar. A quick reminder, you can send in your questions or comments by typing them into the Q&A box on the right-hand side of your screen. You can also visit the handout section on the right-hand side of the screen too, to get content for download and useful resources. Let's start with our first question from the audience.
So the first one, you needed code to make this work. Our lab doesn't have anyone that can do even as much as you showed today. How do we get started? Some of the labeling techniques we showed are accessible even if you don't have anyone who writes code. And it would be worth spending a little bit of time thinking about, what data do I have and can I get some basic organization around it? Label it, organize it, set it up, and see how much you've got. Even that part of the process leads you to some insights. So if you don't have coding in-house, you can get support for that part. But the part that we can never help you with is, where are you going to get the data in the first place? And then maybe the second question here, could this work for spectroscopy data or other non-imaging analytical techniques? Absolutely. We picked images because they are visual and you can see them for a presentation. These techniques are very generally applicable, and absolutely amenable to many, many kinds of data. Please do not think you are limited to images, because that's what we happen to show you today.
Yeah. And I think I can grab this other one. How many images do we realistically need before we should even attempt this? Well, I think that depends a little bit on what your objective is. And I think we've seen that you can start with only a handful, and see where that takes you. Some of these algorithms, and depending on the quality of your images, the variability, you could start with as few as 100 or 1,000 and see where that takes you. But I think you're likely to find that you need more to really turn that into a quality model. But that doesn't mean you can't start, right? And I hope that maybe our last example kind of demonstrated that a little bit. We always tell people this is an iterative process. As you're building a model, you're going to start and refine over time and build that out. And some of that is exploratory, and some of that is sort of human in the middle work, where we're taking the data that we're getting, we're validating that predictions are correct or incorrect, maybe relabeling to fix things that are wrong, and using that data to make that model better, to feed that back. And that's where good, solid project and software development processes can really help to turn the process of developing and refining these models into something that's regular and repeatable, so that over time, even if you start with a little data, be it images or anything else, you can turn that into more and more over time, and let that build better and better models. So I'd say experiment with what you have and see where it takes you.
I think that's what we've got time for.
Mm-hmm.
Thank you all for coming. Laura, any last words?
This brings us to the end of this webinar. On behalf of Lab Manager, I'd like to thank Adam and James for all the hard work they put into this presentation. And I'd like to thank all of you for taking time out of your busy schedules to join us. A reminder that all of the presentations from the AI and Lab Software Digital Summit will be available for free on-demand viewing. Please watch your emails for a message from Lab Manager once these videos become available. Once again, thank you to our sponsors at LabVantage Solutions, Waters Corporation, Cleaneasys, Yahara Software, Millipore Sigma, and Uncountable Inc. Their support allows Lab Manager to keep these digital events free of charge for our readers. Please stay tuned for our next webinar at 3:30 p.m. Eastern, titled Bridging the Expectation Gap, Building a Science-Smart AI Strategy for R&D. For more information on all our upcoming or on-demand webinars, or to learn more about the latest tools and technologies for the laboratory, please visit our website at labmanager.com. Thank you all for being a part of our AI and Lab Software Digital Summit. We hope you have a great day.
Yeah, thank you.